Subject 8, Calculation of Integrals, Part 3, Integrals by Parts. Integration by parts is a technique for integrating products of functions. The integration by parts formula is as follows. We have the integral of one function f of x that multiplies another function g of x and the symbol differential of x dx. Then we choose the function f of x and we denote it by u. And next we pick up the function gx joined with the differential of x, and we denote that block by dv. With this notation is usually how you find the formula in textbooks, and the way it's easier to memorize. And we focus on the u, and we derivate the u and turn it into du. So du is the derivative of f of x times dx, because we are derivating according to x. And next we focus on the dv section of the integral, and we integrate dv and we turn it into a v. So the v is the integral of the function gx according to x, so it's gx dx. Once we've got these two blocks and its corresponding either derivative or integral, then the formula states that the original integral of the two function f times g is equal to u times v minus the integral of v times du. So we pick up the elements in this block, and out of them we build the formula according to the given notation. U times v minus the integral of v times du. Notice that this is again a new integral. This is a new integral that we have to solve. And eventually it could also be a by parts integral. Okay, so let's focus now on the type of integrals that are suitable to be solved by parts, by technique of by parts. Not all integrals are suitable for so. Even if they are a product of two functions, it's not necessary that they are a by parts integral. We're going to study three types of by parts integral. The first type has this particular structure. We're going to have a polynomial expression degree 1 times an exponential function raised to the power of a polynomial expression degree 1 also. Okay. For example, we can have the integral of 2x plus 1 times e raised to the power of 3x plus 4 dx. That's the full structure. Sometimes a number is missing, or the numbers are not integer but decimals, positive, negative, fractions, and so on. But this is the whole structure. And according to this structure, u is always going to be the polynomial expression multiplying the exponential, and the dv is always going to be the exponential plus the d of x. The generalized version of this is when I have a polynomial expression degree 1 times an exponential function like this, but now it's a general base, not just the number. For example, we can have the integral of minus x plus 3 times 7 raised to the power of x half dx. So this is an example of this structure. Polynomial expression degree 1 times an exponential with a general base, not just the number. And again, the choice is same u for both, the polynomial expression multiplying the exponential, and for this general case, again, the dv is the exponential raised to the polynomial expression. Let's solve these two examples according to the formula. Let's start with the e base, and according to the formula, u is going to be the polynomial expression, and we are going to derivate it. Du is 2 times dx. And the dv is going to be the exponential and the dx, and we are going to integrate the dv to obtain the v. So we're going to integrate 3x plus 4 dx. And remember, this is a pure exponential, very easy. And when it's a 3 and a 1/3, usually I'm going to write a different color. And so I've got the derivative of the exponent, and the final result is 1/3 times e raised to the power of 3x plus 4. And now that I have all the 4 elements in the formula, I can write the biparts formula, and it's u times v minus the integral of v times du. And now I can reorganize all these elements and do the final integral. So first part, I've got 1/3 times 2x plus 1 times e raised to the power of 3x plus 4 minus, I write 2/3 outside, then I leave some room for the constant that I need. And again, what I need is a 3 and a 1/3 outside to cancel. So the final result is 1/3 times 2x plus 1 times e raised to the power of 3x plus 4 minus 2/9 times, and now I integrate again, e raised to the power of 3x plus 4, and then plus the constant. And that's the final result of the integral using the biparts technique. Let's see now the example for the general case. Now Ru is going to be minus x plus 3. I derivate, and it's du equals minus 1 times the x. And dv is going to be 7 raised to the power of x halves times dx. I integrate in order to obtain the v, so it's the integral of 7 raised to the power of x halves dx. So I need a 1/2 inside and a 2 outside to cancel with. So this is 2 times 7 raised to the power of x halves divided by the Neperian logarithm of 7. We're ready to write the biparts formula. Is u minus x plus 3 times v, 2 times 7 raised to the power of x halves divided by the Neperian logarithm of 7, and then minus the integral of v 2 times 7 raised to the power of x halves divided by the Neperian logarithm of 7 times du minus 1 times dx. Then I reorganize the expression. 2 over Neperian logarithms of 7 multiplies minus x plus 3 times 7 raised to the power of x halves. Minus minus is plus. 2 divided by the Neperian logarithm of 7 times the integral of 7 raised to the power of x halves dx. Again, I need a 1/2 inside, a 2 outside to cancel with, and the final result is 2 divided by the Neperian logarithm of 7 times minus x plus 3 times 7 raised to the power of x halves plus, and then is 4 divided by the Neperian logarithm of 7 times 7 raised to the power of x halves, and divided again by the Neperian logarithm of 7 plus the constant. And that's the final result. Next, let's focus on second type of integral that is suitable to be solved with the biparts formula. This is the structure given by a polynomial expression times a trigonometric function, where the trigonometric function is the one of a polynomial expression degree 1 again. So as you see, so for example, for the sinus, we can have as example the integral of 2/3 times x plus 1, and then the sinus function of x minus 1/3. And in this situation, always the u is going to be the polynomial expression multiplying the trigonometric function, and the dv is going to be the trigonometric function. Same situation, same type of work applies for the polynomial expression that multiplies a cosinus function. Is always going to be the u block, while the trigonometric function is going to be the dv block. Let's see an example with the sinus function and with the cosinus function. The work will be similar. We start identifying our u expression is always going to be the polynomial expression degree 1 multiplying the trigonometric function, in this case the sinus function. Derivative is 2/3 dx. And the dv, it's going to be the trigonometric either sinus or cosinus function. In this case is going to be the sinus function dx. And I integrate the sinus function and I get the integral of the sinus of x minus 1/3 dx. Derivative of the expression inside the sinus function is 1, so I cancel with 1 outside. It's like writing nothing. So this is a straightforward. The integral of the sinus function is minus cosinus of x minus 1/3. I'm ready to use the biparts formula, and it's u times v times v minus the integral of v times du, which is 2/3 times dx. So we reorganize the expressions, and it's minus 2/3 times x plus 1 times the cosinus function of x minus 1/3. and this minus minus plus the 2/3 outside times the integral of the cosinus of x minus 1/3 dx. Again, the derivative of the expression inside the cosinus function is just 1, so I need 1/1, makes no change, makes no difference. And I'm ready to write the final expression of the integral as minus 2/3 x plus 1 times the cosinus function of x minus 1/3, then plus 2/3 times, and the integral of the cosinus function is the sinus function of x minus 1/3, then plus c. And that's the final result of the integral. And our third and last type of integral by parts is the following structure. We're going to have a polynomial expression, but this time the polynomial expression is any degree, not just degree 1. And it's going to multiply an imperial logarithm of a number times x raised to any power. Both n and m are always natural numbers, so they are integer powers, whole number powers. And this case changes from the other two because our u is not going to be the polynomial expression but an imperial logarithm, and the dv is going to be the polynomial expression, so it's exactly the other way around as before. When we solve our example, we see why the situation is like that. For example, let's focus on the following integral. It's 3x cubed minus 2x squared plus x minus 3. That multiplies the imperial logarithm of 5x squared dx. So that's the structure. Always polynomial expression any degree, and an imperial logarithm of a constant times x raised to any power, but always a positive power and a whole number. So now the formula says that our u, the expression that we're going to derivate, is the imperial logarithm of 5x squared. I derivated, and du is, it's a fraction, it's 5x squared the denominator, and it's 10x the derivative at the numerator. And notice that, and this is important in this case, that we can simplify, and it's highly recommended that you do simplify. So it's 2 divided by x, final result there. And now the dv is going to be 3x cubed minus 2x squared plus x minus 3. And this is the x. And we're going to integrate. V is the integral 3x cubed minus 2x squared plus x minus 3 dx. So this is 3x fourth power divided by 4 minus 2x cubed divided by 3 plus x squared divided by 2 minus 3x. And we are ready to write the by parts formula. So it's u times v. So u was the imperial logarithm of 5x squared times v, the result of the integral, which is 3x fourth divided by 4 minus 2x cubed divided by 3 plus x squared divided by 2 minus 3x u times v minus the integral of v 3x fourth divided by 4 minus 2x cubed divided by 3 plus x squared divided by 2 minus 3x, and that multiplies 2 times x dx. So now, in order to solve this integral, we must multiply this 2 over x times each one of the addends in the polynomial expression. So we have to multiply 3 times x fourth power divided by 4 times 2 divided by x minus 2 thirds times x cubed times 2 divided by x plus x squared over 2 times 2 divided by x minus 3x times 2 divided by x. And now we have 6 over 4 times x cubed minus 4 over 3 divided by x times x squared plus x minus 6, and that's the expression that I have to integrate. For any integral of this type, it's always going to happen the same, that the Neperian logarithms, when we derivate it, it turns into a fraction. When I simplify, it's a fraction with an x at the denominator and a constant at the numerator, like this fraction here. And so when we multiply times the result of the v there, then we will always have to multiply each addend and then simplify in order to get the expression of the last integral. So I copy the first part, 3x fourth power 4 minus 2x cubed divided by 3 plus x squared halves minus 3x, and then minus integral is 6 fourths times x cubed minus 4 thirds times x squared plus x minus 6, and that's the x. And now final result is Neperian logarithm of 5x squared times, and I copy the polynomial expression that makes the v, and I integrate straightforward, and I get minus and parentheses 6 fourths x fourth divided by 4 minus 4 thirds x cubed divided by 3 plus x squared halves minus 6x and plus 6, and that's the final result.